In this video, we're going to look at the Stark effect in hydrogen. We're going to use perturbation theory to sort of look at what happens when we put a hydrogen atom in an electric field. So we know for the Hamiltonian, for the hydrogen atom, just written sort of simply is that kinetic energy plus that central potential. We solved this before and got our hydrogen atom eigenstate. So we have sort of our unperturbed Hamiltonian and our unperturbed states. And the question now is if we apply some external field to this Hamiltonian, well, what does that external electric field do? So if we define that external field, or really the z-axis as being the direction of that magnetic field, what's going to happen to our system? Well, if we really simply sort of model, a hydrogen atom as a, proton and an electron, now those two particles can form a dipole that wants to align along the z direction with the field. The magnitude, so these are going to form a dipole, and the magnitude of that dipole is essentially going to be the product of the charge and the displacement between the two particles forming that dipole, and it's going to be oriented from the negative charge to the positive charge. So that's sort of the direction of our dipole. So if we want to do that, it's going to be, like I said, the charge times the relative position of the electron and the nucleus, but it's rather than being pointed, r goes from the nucleus to the electron, so the dipole is going to be negative of that. So if that's our dipole, our electric dipole of our proton and our electron, we know that the classically the potential energy of that dipole in a magnetic field is just d dotted with that electric field, right? Negative d dot electric field. So our perturbation Hamiltonian is just going to be that, right? That potential energy dotted with the electric field. That electric field's in the z direction. This dipole. So essentially, we get the magnitude of that electric field cosine theta, right? Because we know that A dot B is equal to the magnitude A, magnitude B, cosine the angle between them. Well, in this case, we have the vector, the E field vector has a magnitude of E, and the dipole has a magnitude of ER. And the two negative signs here will cancel. So we have our perturbation Hamiltonian, or we can now write our full system Hamiltonian for our electric, our harmonic, our hydrogen atom in an electric field as this, where this is our unperturbed Hamiltonian, the hydrogen Hamiltonian that we've solved, and this is our perturbation Hamiltonian. So we've sort of set up our problem and sort of defined our Hamiltonian of our system, written it in terms of a solved and a perturbing Hamiltonian. We can now apply our perturbation theory to see how this external magnetic field affects our hydrogen atom. So let's look at the n equals 1, just how does this affect the ground state, right? So if we look at the n equals 1 state and look for the first order energy correction to that n equals 1 n equals 1 eigenenergy, that's just first order perturbation theory tells us that's the unperturbed, it's the diagonal matrix element of our perturbation Hamiltonian, right? So in this case, that's just the 1, 0, 0 state. We take our perturbation Hamiltonian here, e cosine theta, 1, 0, 0. That and that's what we have to solve. That's how that energy, what's going to come of that energy correction. Now we know that our 1, 0, 0 state in the position representation is written as 1 over root pi times a to the 3 halves, um, e to the negative r over a naught. Um, so this is the position representation. We essentially just have to, perform this integral in the position representation to get it. So that first order energy correction, e epsilon cosine theta 1, 0, 0, is going to be the integral of essentially that 1, 0, 0 energy eigenfunction, um, that probability density really squared times e cosine theta dv, right? So we have to perform this integral. What does that integral look like? Well, if we want to write this in a little more detail, or we just go through that, we can pull out the epsilon. We're going to integrate from 0 to infinity in r, 0 to 2 pi in the azimuthal angle, and 0 to pi in the polar angle. We have that r cos theta, and I just realized I have left out an r in all of these little terms here. I forgot to carry it with us. It is, yeah, okay. So thankfully I did include it up here when we actually did the dot product, but forgot to copy it down there. Sorry. Anyway, yeah. So this integral has that r cos theta. That this probability density, it's just the square of this. If we write that out, that is 1 over pi a naught cubed e to the negative 2r over a naught. The volume element in spherical coordinates is r squared sine theta, and then we have d theta, d phi, dr, or split it up into the separate integrals. Over the r integral, we have from 0 to infinity r cubed e to the minus 2r over a naught dr, the polar angle from 0 to pi of cosine theta sine theta d theta, then the integral from 0 to 2 pi of d phi. If we look at this integral and think a bit about it, we can sort of quickly realize that it goes to 0. If we look at particularly this, the integral over the polar angle phi, we see that goes to 0, right? If we just plot a sine function and a cosine function along here, we're integrating from 0 to pi, right? And if we look at, if we cut that in half and look at pi over 2 here, we see that cosine, cosine's even. We have the area under this curve and the area under this curve. It's even about pi over 2, whereas the sine is even about pi over 2, and the cosine function is odd about pi over 2 over that interval. So you put them both together, and this integral ends up being odd about its middle. So you're going to have, the blue area to the left times the red area to the left is going to be positive and equal to the blue area on the right times the right area on the right, which is the same magnitude but negative. Anyway, hopefully you can see that this is equal to 0. So our first order energy correction to our ground state in hydrogen due to this electric field is 0. The electric field has no effect on that ground state of hydrogen. So let's move on to the second energy level. Now we know that n equals 2 state is degenerate, so we're going to have to use degenerate perturbation theory, and we have the degenerate states 2, 0, 0, 2, 1, 0, and then 2, 1, positive, and minus 1, those M states. So we have those degenerate states for the n equals 2 uh, level in hydrogen. Degenerate perturbation theory essentially says we have to, we know our degenerate subspace, the space spanned by all of these. We need to diagonalize the perturbation Hamiltonian for that subspace. So there are 4 states here, right? One, 2, and then these 2, 3, and 4. So this is going to be a 4 by 4 matrix that we have to diagonalize. Each one of those matrix elements is going to be an integral over these position, we're going to have to do an integral over the position representation of these wave functions, which, maybe I won't write them all out here, but are unperturbed position wave functions. The first one, just 2 over 2 a naught to the 3 halves. These are not simple integrals to do necessarily, right? R over 2a naught 1 over root 4 pi. And then these ones we're getting, similar complicated position position representation or wave functions for these. We have to do a 4 by 4 matrix, each element being that's 16 big integrals. That may seem pretty daunting and tedious to do. However, we can take advantage of some of the properties of these wave functions, in particularly the fact that all these wave functions have a definite parity that we can use to show that a lot of those elements in that perturbation matrix are going to be 0. So, excuse me. So what was the parity of these things? If you recall, the hydrogen wave functions, the parity of them was essentially determined by that L quantum number, right? So the independent of M or N, if L was odd, they had odd parity. If L was even, they had even parity, right? So what does that mean for our integrand for those matrix elements, right? So if you recall, we're looking at matrix elements that have sort of this form, right? Where those matrix elements are N, L, M, E, epsilon, R, cos, theta times N, N 2, L 2, M 2, and these are NL 1, 1, 1. So we're looking at those matrix elements. Well, if this part, this is odd, right? These wave functions, if they have the same L, they're both going to, even if L is odd, the integral is going to be involve R cosine theta. Our wave function, we'll just do this, N1, L1, M1, R, get rid of that, times the wave function N2, L2, M2, R, dV, right? This, if the L is the same, if L is 1 and 1, then we have 2 odd functions multiplied together. That would be even. If L was both even, they're going to be even. Because of this term, which is going to be odd, that whenever L is the same, this integral is going to be odd, and it's going to go to 0. So if we look at that perturbation matrix in the degenerate subspace, right, we can write that. We're going to write that in a basis defined by we're looking at the n equals 2 degenerate subspace. So our basis involves L and M quantum numbers. We have the 0, 0 state, the 1, 1 state, the 1, 0 state, and the 1, negative 1 state, or 0, the rows in the same order. All of the states where we have, the L equals 0 in 0 lineup, that's going to be 0. for the L equals 1, all three of these columns and all three of these rows, that whole subspace is going to have zeros because of that parity argument we just made. So we've already eliminated having to do the bulk of our integrals, and the only possible non-zero elements of this matrix are the ones where we're looking at the coupling between an L equals 0 and an L equals 1 state. We can make our lives, easier again by noticing that this perturbation, it depends on r and theta, but there's no phi dependence here, right? And we know from when we looked at the hydrogen atom, our theta phi energy eigenstates, had sort of three parts: the radial part, and then the spherical harmonic part, which look like this. And these phi these phi eigenfunctions, they went like e to the I m phi, right? And they were orthogonal, right? So the integral here is just going to be over the phi that azimuthal angle is just going to, it's going to go from 0 to 2 pi of those wave functions, which are going to have the e to the negative I m phi and e m1 e to the I m2 phi d phi, right? Or it's going to be, which is equal to the integral of e to the I m2 minus m1 phi d phi from 0 to 2 pi. And that's a Dirac delta function between m1 and m2. Unless those m quantum numbers are the same, that integral is going to be 0, right? So again, if we go back to our matrix here, our perturbation matrix in the spaces, unless we have an m, unless we have the m states match, those elements are going to be 0. So if we look at those, we know that the 1 and 0 state, that's going to be 0. The negative 1 and 0 state, that's going to be 0. Likewise here and here. And we're left with only two elements that we actually have to calculate, right? So the only elements that we have to actually figure out for our perturbation matrix are going to be the 2, 1, 0 state coupling to the 2, 0, 0 state. Those matrix elements. That's the only integral we have to do to figure out in our perturbation matrix. So let's go through and do that integral. So the matrix element we're trying to calculate is this. We know that the 2, 0, 0, the unperturbed 2, 0, 0 state, the wave function for that is 1 over root pi times 1 over 2 a naught to the 3 halves, 1 minus r over 2 a naught times e to the negative r over 2 a naught. And our 2, 1, 0 wave function is equal to 1 over 2 times root pi, 1 over 2 a naught to the 3 halves r over a naught e to the negative r over 2 a naught cosine theta. So if we take those and do that in the position representation, our matrix element ends up looking like this. I have a feeling I'm going to need some more room here. Equal to integral phi to 0 complex conjugate of that times our perturbation er cos theta 211 wave 210 rather wave function times the volume element r squared sine theta d theta d phi dr. If we plug in those wave functions that we just went over, we can pull out all sort of the constants that come out from the wave functions in that, and we get E epsilon 2 over 2 A naught to the 3 halves, 1 over square root 4 pi, then 1 over root 3, 2A naught to the 3 halves, square root 3 over 4 pi, and then the actual integrals, the r integral from 0 to infinity of 1 minus r over a naught e to the negative r over 2a naught, r to the 4 dr, integral 0 to pi, the polar part, cosine squared theta sine theta d theta, and then the azimuthal part from 0 to pi, 2 pi rather, d phi. This integral is easy, just gives us 2 pi. If we then move over and do the theta integral, we have integral from 0 to pi cosine squared theta sine theta d theta. We do substitution, 0 to negative 1 u squared du, where we've made the substitution of, u is equal to cosine theta, so du is equal to negative sine theta d theta. We make that substitution, we get that this integral ends up being just u cubed over 3, evaluated from 1 to negative 1, sorry. This should be 1. You do that integral, and we end up with 2/3. That's what the this polar integral is. So all we have left now is to do this r integral. That r integral is just going to be integral from 0 to infinity, 1 minus r over 2a naught e to the negative r over a naught r4 r to the 4 dr. This splitting it up, r to the 4 e to the negative r over a naught, sorry, dr, 0 to infinity minus integral from 0 to infinity r to the 5 over 2a naught e to the negative r over a naught dr. We can look up these integrals. If you look in the appendix F, it's got some nice integral table. But you can see that from 0 to infinity, x n e to the negative ax dx. That integral is equal to n factorial over a to the n plus 1. So if we can use that to do both of these integrals because they have that form, and these integrals, this r integral. So let me just box this so we know we're using it. These integrals end up being, well, this would be 4 factorial times a naught to the 5, and this integral would be 5 factorial over 2 a naught times a naught to the 6th. And if we carry all those through and do all of it, we end up with negative 36 a naught to the 5th is what that our integral looks like. So bringing this all together, our matrix element that we're trying to calculate, that 2, 0, 0, that perturbation element of our matrix, if we go all the way back up here to what we had, we can simplify all this stuff and then plug in what we got for those integrals. We end up with E epsilon over 4 a naught to the 4th times 4 pi over those factors. That our integral is this negative 36 a naught to the 5. Our polar angle was that 2/3, and our azimuthal integral was 2 pi, right? So this whole thing ends up reducing to just negative 3 e a naught is our matrix element, and we've got now. So after all of that integration, we did, you know, we worked smarter and not harder and used parity and the orthogonality of the azimuthal wave functions to make to sort out that a bunch of those matrix elements were 0, and then we only had to do that one whatchamacallit, integral that we just went through, and we've got that our perturbation Hamiltonian is negative 3 e epsilon a naught, and then 0, 0, negative 3 e epsilon a naught, and then zeros everywhere else in this perturbation matrix in our degenerate subspace. Now we have to be careful here. I've sort of switched the way I've written it, and way up here when we first introduced this matrix, I was using our basis states in this order: 0, 0, 1, 1, 1, 0, 1, negative 1. I've switched it to sort of, you know, put the coupled states next to each other, but the L and M values of in this basis are 0, 0, 1, 0, 1, 1, and 1, negative 1. Or if we were to do it along, call the rows 0, 0, 1, 0, 1, 1, 1, negative 1. So these, you know, the matrix elements that are non-zero are coupling the 1, 0 and the 0, 0 states together. So that is the matrix, and that is our perturbation in our degenerate subspace. And degenerate perturbation theory says what we have to do is to diagonalize that Hamiltonian in the degenerate subspace. So what we do, you know, we take the determinant. What we're doing is taking the determinant negative lambda, negative 3 e a naught, 0, 0, 3 e a naught minus lambda, 0, 0, 0. And, you know, this is one of the benefits of writing the Hamiltonian in the basis that we wrote here, where we switched the order of our basis states, is this determinant is a lot clearer on how to calculate it. That determinant gives us, you know, lambda squared times lambda squared minus the 9 e squared a naught squared. And this has to be equal to 0. And when we look at that, we have our eigenvalues end up being plus or minus, you know, either this is equal to that, so our eigenvalues are plus or minus 3 e epsilon a naught, or there's 2 zeros there. So we have the corrections, you know, and when we diagonalize that, those end up being the corrections to our energy eigenstates in degenerate perturbation theory. So what we end up having is, and the other thing that's great is we can also associate that these L equal 1 states and all that are not perturbed. We can identify that this is the subspace. Sorry, let me say that a little clearer. These are the states that are going to be corrected in that subspace. This matrix is sort of diagonal in this subspace, right? So the states that are made up by these are not the ones perturbed. These m equals 0 states and are the perturbed ones. So if we want to know how that electric field affects the energy levels of our hydrogen atom, well, we knew that the unperturbed energy level in hydrogen for the n equals 2 state was just that negative 13.6 eV over 2 squared, or 4. We have 4 states that are degenerate in that. 2 of them stay the same and have no shift, right? So we have E2, we'll call it E2A, to first order is just going to be that negative 13.6 over 4 EV. That's also going to be equal to one of the other states in that from that system and from that degenerate subspace. But then we're going to have one state is going to go up. We'll call that one E2 plus. It's going to be negative 13.6 EV over 4, and it's going to go plus 3 E A naught, and one of those n equals 2 states is going to go down, and it's going to have an energy of 13.6 EV over 4 minus 3 E epsilon A naught. So, if we were to plot those as a function of that electric field strength, we have our n equals 2 unperturbed state. 2 states just stay flat like that. One of the states gets larger in energy, one of the states drops in energy. To figure out what those perturbed states look like, again, we're diagonalizing this perturbation Hamiltonian in our subspace. We already know, as I mentioned before, that this is already diagonal in this subspace. So we know that the L equals 1 and m equals 1 and the L equals 1 and L equals minus 1 states are not perturbed by this. And it's this sort of 0, 0, L equals 0, m equals 0, and L equals 1, m equals 0 subspace that we have to diagonalize to figure out what those perturbed states look like. To find those states, we're essentially looking at, the eigenvalue equation for that those energy for those perturbed energies, right? So if we look at this, in that subspace, this is that 0 for the plus 1. This is going to be plus 3 E epsilon A naught, 3 E epsilon A naught 0 times some AB is going to be equal to that E plus AB. We have that eigenvalue equation where these are the A plus, it's going to be some combination. The states are going to be some combination of these 2 states that are coupled by that perturbation Hamiltonian. So these are the coefficients of that states. This equation gives us 3 E epsilon A naught times A plus, B plus. I know how to do matrix math. Is equal to 3 E epsilon A naught, that A plus, which is essentially, this is my mistake. These are -3. I'm writing the perturbation matrix. So these are negative. The eigenenergy we're looking at is positive. So this first line of the equation gives us that, which tells us that negative B plus is equal to that A plus. So our and then normalization tells us that these are going to have magnitude of 1/√2. So the first order, the perturbed state for that E plus, for that state that goes up, is going to be written as 1/√2, 1 minus 1 is going to be that normalized state. We do the same thing for E minus, and the only thing that's going to change is this is going to become negative. We're going to get the E minus state is equal to 1/√2, 1, 1. So going back to here, so writing these with using the actual basis states that we wrote our Hamiltonian in, these ones, this means that the state that goes up, that E plus state, is 1/√2, 2, 0, 0, minus 2, 1, 0. It's a combination of those two states, and the E minus state is 1/√2, 2, 0, 0, plus 2, 1, 0. So those are the two states. If we look at, this plot here, that's our E plus state goes up, our E minus state goes down, and our the states that stay the same are that 2, 1, 1 and the 2, 1, -1 states. So what does this all mean? Essentially, applying this electric field to our hydrogen atom sort of took our n equals 2 states. It left these two the same, but it took that S and P0 states, that L equals 1 and M equals 0, and our L equals 0 and M equals 0 states, and coupled them together, and those states have essentially a dipole moment. Those coupled states have a dipole moment. The E plus and E minus states just correspond to, if you think about it classically, the states that are aligned, where that dipole moment aligns with the electric field or anti-aligns with that electric field. And that's what we have. Hopefully you followed along and this is making sense. But a nice, I think, example that we hopefully we can all work through. Apply an electric field to our hydrogen atom. N equals 1 state is non-degenerate, so we apply non-degenerate perturbation theory. See, it actually isn't perturbed by that electric field. Look at the N equals 2 states and apply our degenerate perturbation theory and come out with that sort of coupling between the S and the P0 states. If you have any questions, email me, bring them up. We'll discuss this and other examples more in the synchronous sessions. I will see you there.